We present GANViz, a visual analytics system for machine learning experts to evaluate, interpret, and analyze generative adversarial networks. GANViz consists of the following 5 components. A metric view, showing the overall quality of a GAN model with focus plus context line charts. A probability view, demonstrating the performance of the discriminator with confusion matrix information, and thumbnails showing the trend of visual features. A distribution view, presenting the generated images, their feature distributions, and their probability distributions in comparison with the real images. A tensor path view, enabling users to conduct detailed investigations on the discriminator's neural network architecture. An activation comparison view, allowing users to perform comparative analysis across image sources and timestamps. We now demonstrate how GANViz works by analyzing the DC GAN model with the MNIST data. We target to demonstrate how GANViz satisfies the requirements from domain experts in 3 themes: model evaluation, model interpretation, and comparative analysis. From the metric view, the losses of the generator and discriminator were very high initially, but they dropped quickly after several batches. We can also see that the generated images at the very beginning are just random pixels. With the training process moving forward, we can see that the generator can gradually generate blurry images of digit 1. We can also switch to other digits to see the appearance of generated images. When we come to epoch 1, the focus part of the metric view enlarges the losses of the discriminator and generator in this epoch, and from there we can see the complementary pattern between the 2 loss curves. In the radio button on the top, we can see the trend of the 3 metrics we introduced in the paper. Mode collapse did not happen as the diversity curve keeps consistently high. The area of the curve is slowly increasing, which indicates that the discriminator strives to improve its performance. Meanwhile, the curve representing the distance between the true data distribution and the learned distribution is declining in later training stages, indicating the model progresses in the right direction. From the probability view, we can see the 2 probability curves for sampled images from real and fake data. The 2 rows of thumbnails reflect how the visual features change with the decreasing of the corresponding image's probability. Here, images with italic style received higher probability to be real. During our explorations, we found that the discriminator prefers different features in different timestamps. For example, images with italic style received lower probabilities. We can also see the distribution of images in the confusion matrix. The area under the curve value for the discriminator is 0.62 currently. Clicking on the area under the curve button will show you the details of the ROC curve and the AUC area. Although the generated images are still blurry in this timestamp, we can see that images with italic styles have successfully cheated the discriminator and received higher probability values. The probability of images without italic styles, however, is very low. The same is also true for the real data. As the discriminator is very biased toward the italic style of this timestamp, the colored squares show very uneven distribution. One important question our domain experts want to investigate is how the discriminator could differentiate the vertical and italic styles in one timestamp. To answer this question, we can select images with representative features into the tensor path view for detailed analysis. Here, image 180 and 66 are selected to represent vertical and italic digit 1, respectively. As we can see, the neurons lead to the most different activations is neuron 3 and 0 in this timestamp. As this is still in the early stage of the model, we would like to first track several epochs of these 2 digits to find out how the importance of neurons change over time. The training stage can be changed by brushing the desired epoch or batch in the metric view, and the same 2 digits at different stages can be added by their index. The record button records activations in the current timestamp into the activation comparison view. By hovering over activations in the activation comparison view, we found that neuron 2 and 6 become the most important neurons in differentiating image 180 and 66 since epoch 5, and they keep being the most important neurons. Going back to the tensor path view, we can hover over these 2 neurons and their corresponding activations to figure out the effects of neuron 2 and 6. it can be seen that neuron 2 is a horizontal filter from left to right, which can extract the pixels on the left side of the vertical in italic digit 1. The difference between positions of these highlighted pixels makes the discriminator differentiate these two digits and get different probability values to them. Neuron 6 can be analyzed in the same way, and the details can be found in our paper. Domain experts are also wondering if neuron 2 and 6 are important in differentiating vertical and italic images of other digits. Here we compare images of digit 0, 1, 2, and 3, with and without italic styles. From the activation comparison results, we know that neuron 2 and 6 are also important in differentiating other vertical and italic digits. Another interesting question from the domain experts is whether the discriminator uses the same neurons to differentiate vertical and italic images from different sources, such as the images from the training set or images generated by the generator. This view compares 4 rows of activations representing images from different sources in different categories. We can see that the 4 orders of neurons in differentiating the 4 pairs of vertical and italic digit 1 are mostly the same, which indicates that the discriminator treats images from different sources equally. We have also explored GANViz with the Google Quick Draw data. Details about the explorations can be found in our paper. Thank you for watching.